Cylinder fit, easy axis calculations. A very common issue when surveying tubular objects to determine their axis is the lack of a reliable reference for collecting circle points in a plane perpendicular to the cylinder's axis. If a weld is visible, it can serve as a good reference, enabling 3D circle fitting, finding the circle's plane perpendicular to the cylinder's axis and fitting a 2D circle in that plane. However, this is rarely the case. Most often, no weld or visible reference line on the tubular can be seen, or it is difficult to identify. The classic approach is to survey circle points by eye, attempting to position them in a plane perpendicular to the axis of the tubular. Then, during post-processing, the circle is calculated as a two-dimensional circle in one of the three major planes, XY, XZ, or YZ plane, assuming that the tubular's axis aligns with one of the three principal axes, X, Y, or Z. This approach can work, but only when surveying horizontal or vertical tubulars relative to the coordinate system. Even then, it's still just an approximation since inclination of the tubular is unknown. If it is significant, and especially when points are collected from one direction, which is most of the time a case, the projection of collected point on the assumed plane will be closer to ellipse. Using circle fit algorithms then will introduce shift in the circle center and incorrect axis of tubular. What is the best practical way to obtain the axis of a tubular then, and how should it be calculated? If there are visible welds, the answer is to survey them and use 3D circle fitting to obtain the circle centers and, effectively, the axis of the tubular. If the welds are not visible or are difficult to identify, survey circles on the tubular by eye, close to the plane, perpendicular to the tubular's axis, and then use an iterative calculation process to determine the axis. Here are iterative steps. Let's see the hard way first. Calculate rough 3D circles, at least two, and determine an initial axis for the tubular. This may be quite inaccurate initially. Align this axis with one of the major axes of the coordinate system, for example, x-axis. Perform 2D circle fitting in the YZ plane to recalculate the tubular circles and derive a new axis. This will already be a significant improvement. Use new circle centers to align the new axis again with the x-axis. Repeat the 2D circle fitting. Continue this process until the differences in the coordinates of the calculated circle centers become minimal. Transform back to the original coordinate system. This is the correct way to calculate the axis of a tubular, but the process is tedious and time-consuming in post-processing. It may require many iterations, depending on the number of circles used and how small the coordinate differences need to be to stop the iteration. But now, this process is history. DimConIt 2025 offers a powerful tool that automates the entire procedure: cylinder fit calculations. Simply select all your surveyed circle points from Detected Objects table and click the Cylinder Fit button. All circles will be calculated in described iterative process until the best fit axis achieved. Circles and line axis are added to the project on exit from the calculation window. The module is very powerful, reducing processing time to just seconds while still providing extensive control over the calculation process. When more than two circles are used for axis fitting, a 3D line fit algorithm is applied to achieve the best possible line fit. The radius can be fixed in three ways: directly in the options menu for all circles at once, individually for each circle in the calculation table, or in the circle calculation window opened by double-clicking the circles row in the table. Circles can be reviewed individually. Or automatic filtering can be applied to exclude bad points. Filtering of the circle centers used for the line fit can be done either automatically or manually. A report can be generated for each calculation. As usual, the solution provides full numerical information about its quality, the number of iterations and points used, as well as data such as line length, endpoint coordinates, and line attitude, pitch, roll, and inclination. Upon exiting the module, the user can choose to add only the axis or to add both the axis and the circles, with the option to review each individual circle. To summarize, the cylinder fit module delivers a fast, precise, and fully automated way to calculate a cylinder's axis using an advanced iterative method, ensuring the most accurate fit possible. It not only saves a tremendous amount of processing time, but also offers full flexibility and control over every step of the calculation. With options for both automatic filtering and manual overrides, it adapts perfectly to any project's needs, combining speed, accuracy, and user control in one powerful tool.